Hello everyone, welcome to lecture 2 of week 7 of the course Power Network Analysis, in which we will start with a new interesting module which is going to be power flow analysis. And the first lecture of power flow analysis, we will try to understand that the basic circuit principles that we have been so well aware of, specifically the use of Kirchhoff's law, nodal analysis, mesh analysis. Why can't the same basic circuit analysis for circuits where the sources are in terms of voltage and current, why can't the same be done for the actual power network? Why do we need this power flow analysis at all? So that we will discuss in the current lecture. So far, we have been able to cover 5 initial modules, starting from basic circuit principles to transformers, the importance of per unit analysis. From transformers perspective, we understood how do we model or understand single phase transformers, what are 3-phase transformers. Then we went into synchronous generators, and finally the last 2 modules was all about transmission line. How do we evaluate the corresponding parameters of transmission line and make use of those parameters to come up with certain steady state models for transmission line, which can be used to understand their performance under different operating conditions. So, basic circuit analysis, if we see from the perspective of the power network or power system, our power system or network is a highly interconnected man-made network which consists of several electrical components ranging from generators to step-up transformers. The generators are the sources of the power which are essentially consumed by the loads or the consumers here. And since power cannot be transmitted to far off lengths at low voltages, where typically generators generate this power in few tens or 20s of kVs, the same power, if it were to be transmitted to far off distances to the load points, then the losses involved will be very high, the voltage drops would be very high, and hence we need step-up transformers to boost up the supply voltage or the source voltage, and from then the stepped up voltage or power flows through these transmission lines. The devices here refer to the reactive power compensation devices, FACTS devices, STATCOMs, SVCs, etc., which help in proper reactive power compensation and maintaining voltage profile along these 3-phase transmission lines, where operating voltage is in order of few 765 kV, 400 kV, etc. for Indian system. And at the same voltage level, again, these loads or consumers cannot consume power, so we need step down transformers to boost down the voltage or step down the voltage, and then from the substations the distribution network comes in, from where the loads get their power from. So essentially, this complicated network, it can again be represented as a basic circuit whose topology is known. That means how the lines are connected, where the sources are present, where the loads are present. And if we know the network parameters in terms of line parameters, and also the fact that the sources are known in terms of voltages and currents, then the resulting equations which would be involved for analyzing this given circuit would essentially turn out to be few set of linear equations based on the Kirchhoff's current law, Kirchhoff's voltage law, Thevenin's theorem, nodal analysis, mesh analysis, and so on. So is that still true for the given power network? Let's see that. So to begin with, I'll try to explain the basics of nodal analysis and mesh analysis, and then we'll see whether these can be used for the actual power network. So given a circuit, if we have to analyze it by nodal analysis, so I have considered one such circuit where there are 5 distinct nodes. The nodes are node A, whose voltage is VA, node B, node C, node D, and node E. And if I understand or figure out the voltages of all these nodes, then basically I can find the currents through each of these circuit elements, which could pertain to a typical conductor or a transmission line connecting two such nodes or buses A and B in the actual power network. And in this circuit, there are also sources present whose specifications are known in terms of the specified voltage. So by nodal analysis, we can find the unknown node voltages, and these unknown node voltages would be obtained from a set of linear equations, which would be obtained by application of KCL and KVL if required. So since we have 5 nodes, so our aim here in nodal analysis is to find these 5 node voltages. Now when we say that the circuit is known to us or given to us, where the resistive elements are all known, 10 volt source is given, 5 volt source is given. We also have to understand that the node voltage, let's say VA, if we have to find its voltage, voltage always is a form of potential difference. That means there has to be 2 points between which this voltage or potential can be measured. So in this given circuit, if we have to find these 5 unique voltages, we have to choose a reference for measuring these voltages first. Given the circuit, it's convenient to choose node E as the reference or the neutral point or the ground point from where the potential can be measured. And if we choose node E to be itself the reference, that means the node voltage VE is equal to 0 volt, considering it to be equal to the ground voltage or the neutral voltage. And essentially now we are only left with 4 unknowns: VA, VB, VC and VD. If we have 4 unknowns, we need at least 4 equations, 4 unique independent equations to find these 4 unknowns, and those 4 equations would be obtained by use of the nodal analysis. Also, if we see, there is some specificity about node B and node C. Node B and node C actually form a supernode. And the reason why node B and C together form a supernode, and that's the reason why this encircled dotted portion refers to it as a supernode, because in this supernode there is only a voltage source which is present, which is correlating node B and node C voltages. So essentially, if we apply KVL across this supernode, then essentially we would get VB is VV minus 5 volt, or let's say everything is in voltage. So VB minus 5 is equal to VC. We are starting from node B, traversing along the node voltages potential. So we get a minus 5 here because we are crossing from plus to 5. And essentially when we reach the other node C, we get VB minus VC minus 5 is equal to VC. So probably this could be one of our equations from which we could find the corresponding other 4 unknowns. So given that node E is the reference, if we apply same KVL between node E and node A across this path, then essentially if we start with VE, we jump from minus to plus sign, so we gain a potential of 10 volt, and essentially we reach node A, which is VA. So this is the KVL equation. Since VE is equal to 0, so VA turns out to be 10 volt, and as I mentioned, B and C together form a supernode, so we get this equation in form of equation number 1. So we have got now 3 unknowns left. VA is also known, 10 volt, VB, VC, VCD we need to know, so we need 3 equations. If we apply KCL at nodes B and C, that means if we have nodes B and C, so we apply KCL at node B first, then there are 3 branches which are pertaining to node B. With this is one branch, then we have the other branch between B to C to D, and lastly the third branch is from B to E. So if we apply KCL at node B, and VA is the potential at node A, VB is the potential at node B. So across this particular branch, the current that would come in would actually be VA minus VB by 2 ohm is the impedance. And since this is the incoming current, by KCL, the sum of currents going out should be equal to sum of currents coming in. So the sum of current which are going out for branch B to D, we would have VC minus VD as the current by 1, which is the current over here. The same current would also flow through this voltage source. It's not important to find the current in terms of VB, VC, but VC, VD would give us that current. And lastly, we have the last current, which is VB minus VE by 8. VE is 0, so we have VB by 8 only as the last term. So if we rearrange terms, we get our second equation. Similarly, if we apply KCL at node D, we get the third equation. We have got our equations 1, 2, and 3. Essentially, we are left with only 3 unknowns. We solve these 3 simultaneous equations, we'll get our remaining node voltages, and from there, those node voltages, if we apply KVL, we could find the corresponding currents through individual resistances, impedances, and so on. It's important to note that if one were to figure out what is the current which is being delivered by this 10-volt voltage source, so essentially we would apply KCL at node A. When we apply KCL at node A, we see that there are 2 currents which are going out of node A. One current is 1.36 amperes, which is the current evaluated over here. And the second current is 0.52 amperes, which is the current across the 2 ohm resistor. So essentially, the current I from the 10-volt source by KCL should be 1.36 plus 0.52, which is 1.88 amperes. And similarly, if we see what is the current from the positive potential terminal of the 5-volt voltage source I5, and on similar logic, if we apply KCL, since across the 5-volt voltage source between B and C is a super node, so the same 0.6 current has to flow, so we have 0.6 amperes current. And given these currents, we can probably also find, since this is a DC circuit, voltages are all DC sources, they are ideal independent sources. So if we want to find the power which is delivered in this DC circuit by the 10-volt voltage source, it would nothing be but 10 into I10, which is going to be 18.8 watts. And similarly, if we want to find the power from the 5-volt voltage source, this would be 5, the potential difference across the voltage source, multiplied by I5, which would be 3 watts. So essentially, real power which is being generated together by the sources is P10 plus P5, which is 21.8 watts. Please check that the same quantum of power is also being consumed by these resistors which are carrying this amount of current. Please verify that. For a given resistor, if the current is known, then the power absorbed is nothing but individually it is I square into R, where I is the current through the resistor and R is the resistance value itself. So basically, if we want to find the power which is being consumed or absorbed by this particular 4 ohm element, it would be 1.36 square into 4 watts. Please evaluate this element or quantum for all such resistors, 5 remaining 4 resistors, add them up, it should match with 21.8 watts, because again, by conservation of energy, power or energy cannot be generated or destroyed. Everything has to be properly accounted for. So whatever is being generated, the same quantum of power is also being absorbed by these particular elements. Please keep this idea in mind. This accounting between power generated, power consumed, power lost, power absorbed, etc., would become very important when we understand or go deep into power flow analysis, where we would actually understand the differences between power generated and power consumed. These 2 quantities would hardly ever match for a given AC network because of the inherent I square R loss that would happen in the transmission network. So please keep that thing in mind. The next analysis is the well-known typical analysis is a mesh analysis. Here I have considered a little different circuit. Essentially, it's a AC circuit where you could see the sources in terms of the voltage source as a reference. We also have a current source which is also considered to be as a reference. Both are being measured at the same reference. So these are all phasors. And instead of having pure resistors as impedances or branch impedances, we also have capacitive elements as well as inductive elements. I've just marked them through certain blocks. I have not shown the corresponding capacitors or inductance symbols. And also we have current dependent voltage source. We also have current dependent current source. So basically this is a current dependent voltage source, and this symbol here refers to a current dependent current source. And since these two are dependent on the current I naught, which is the current through the 4 ohm impedance. So that's where the dependency comes in. Again, these sources here, they are ideal sources. Their internal resistances are 0. So all that has not been considered for the sake of simplicity. And we want to find or apply mesh analysis, and we want to find the current in each of the 4 meshes. Now, if we observe this circuit or understand this circuit, mesh analysis also involves finding unknown mesh currents through set of certain linear equations which are obtained by applying KVL and sometimes KCL for super meshes. So, the 4 unique meshes which this circuit has are the ones which are shown over here: mesh number 1, mesh number 2, 3 and 4. In mesh analysis, we first assume what is the current or the fictitious current present in these meshes, and then we try to understand, is there a way to find I1 to I4 currents. So, if we understand these or know these meshes, then it is very clear that in mesh 2, if this current I2 has to flow, this current cannot be different from the source current which is present in that particular mesh, and that's the reason why if I2 has to flow through this particular current source, this I2 has to be equal to 6 ampere, and that's the reason why in mesh 2 I2 is known. And similarly, if we look at the current in across node A and B, wherein we want to find I naught, then I naught can be found basically by applying KCL at node A. So, if we apply KCL at node A, we have to first figure out what are the branches and the currents in which these currents are flowing. So, the incoming current at node A is I2. The outgoing current over here is I3, and at the bottom part A to B it is I naught. So, if you apply KCL, it is I2 is equal to I3 plus I naught, which can be rewritten as I2 minus I3, and since we know I2, so we can find I naught in terms of I3. And similarly, if we see meshes 3 and 4, together meshes 3 and 4, they form a super mesh. So, if we apply KVL, why do these form a super mesh? Because in between these 2 meshes, we have a current source present. This current source essentially represents the fact that these 2 meshes are interconnected or interlooped, and that's the reason why it is called together as a super mesh. Mesh 3 and 4 together form a super mesh. And if we apply, we have to find a relevant number of equations. So, if we use KCL at node B, we get equation 4. If we apply KVL across the super mesh, we get equation number 5. We have got our 3 equations which are basically 4 and 5. So, we have the third equation, which is the equation present over here. We know what is I2. We want to still find what is I1, I3 and I4. So, if we solve equations 4 and 5, from there we get I3 and I4. And lastly, for I1, we apply KVL in mesh 1, which is this KVL. And from there we can find corresponding current I1 also. So, given this particular mesh, we can apply mesh analysis and find all these individual currents. In this perspective also, you can figure out what is the total complex power which is generated by each of the sources, wherein you would basically make use of the fact that voltage from the particular voltage source or current source into the corresponding current conjugate is the net complex power generated. This should match with the complex power which is being absorbed together by elements encircled over here. All these elements, if we try to find their corresponding complex power combination, because now we have a AC circuit, all these 6 elements, their complex power absorbed together should match the complex power generated by the sources of 24 volt, 6 ampere, the current dependent voltage source and the current dependent current source. So, please do ensure that the way we did it for nodal analysis. Coming to power flow analysis, the question remains is, cannot a similar circuit analysis be applicable for the interconnected power system? Probably yes, it should be possible, but the major hurdle which comes in applying the circuit analysis for interconnected power system is that The sources, unlike in the previous circuits, where we had assumed them to be current voltage or current sources, in actual power network, our sources are not known in terms of only voltage and current sources. In fact, they are specified in terms of real and reactive powers, basically, not purely in function of current and voltage. And to be specific, most of our nameplate rating specifications that we see for electrical equipments, you would find two quantities common in all nameplate specifications. They are the corresponding apparent power S, which the machine or equipment can handle or generate, and the corresponding rated voltage at which it should ideally operate. So typically the sources, they are known in terms of power and voltage, not purely in terms of current. And since power and voltage, they are interrelated in some form, as power is equal to product of voltage into current. So resulting equation which comes in from power's perspective inherently tend to be nonlinear equations, and hence, since the equations no more remain linear, the laws, the KCL, KVL, Thevenin network theorem, nodal analysis, they still hold true, but the application of these corresponding theorems don't result into linear equations, they result into nonlinear equations. And that is where the importance of power flow analysis comes in. Power flow analysis also tries the same objective, that is, to solve these nonlinear equations to find steady state system states. We call these to be system states because if we know the voltage phasor of every such bus in a given power network, we can find the currents through the branches, we can find the power consumed, power absorbed, etc., etc. And that's why these are called as system states, which are nothing but the bus voltage magnitudes and phase angles with respect to a particular reference. Basically, we want to find bus voltage phasor at all buses in the given power network, and to find that we have to solve certain nonlinear equations, and the process of solving this is essentially understood in this notion of power flow analysis. For understanding power flow analysis, for applying power flow analysis, there are certain information which is needed. The information which is needed are the bus injections should be known. That means the corresponding source power should be known, the load power should be known, the power network parameters should be known, the line parameters should be known, how the line is connected, whether it is 80-kilometer line, 120-kilometer line, or it is getting tripped off in between. The topology also has to be known. So certain assumptions which go well before one understands why power flow is to be solved or how it is to be solved. Essentially, why power flow is to be solved, we have briefly touched upon that. The answer for that is that we want to find all system states, and how it is to be solved we still have to find. But where does this power flow analysis solution help into? We'll see that in a few moments, or probably in the next lecture. So certain assumptions which go well before we understand how power flow analysis is done is that we assume the system to be in steady state. There are no faults, disturbances, transients happening. The network is perfectly balanced, and the entire network with all its elements can be represented in a per phase analysis through a single line diagram. Generators are represented as constant real power sources with specified terminal voltage. Why real power? Please have patience, we will understand that in a moment. Lines, transmission lines, they are transposed, balanced, and typically represented through the nominal pi model with series impedance and line charging admittance, as we have seen in the previous module. Line shunt conductances are negligible and hence they are neglected. And transformers, yes, they also need to be represented, and there needs to be a special consideration for these transformers when the tap positions are called as the off-nominal tap. We'll see what is meant by this nominal and off-nominal tap in probably the next set of lectures to come in. So these transformers, as long as they are represented in per unit basis, if you recollect the per unit analysis which we saw in our second main module, the impedance of the transformer, be it seen from the primary or secondary side, remains the same. So we call the tap position to be at a nominal position when the tap setting is equal to 1 per unit. 1 per unit tap setting does not mean that the turn ratio of the actual transformer is equal to 1. Basically, if there is a transformer whose turn ratio is equal to 1, it would mean that there is no need of a transformer at all. In per unit, this ratio is equal to 1, which means, let's say if we have a 33 by 415, 33 by, let's say, 220 kV transformer, and if we choose the base voltage on the low voltage side to be 33 kV, recollect that in per unit analysis, the HV side voltage has to be the same as per the nameplate rating, so it has to be 220 kV. If we convert these low voltage into the corresponding per unit, we would have 1 pu. Similarly, VHB would be 220 by VB, which is again 1 pu, and if we take this ratio now, the tap ratio turns out to be 1 per unit. So as long as the tap ratio is equal to 1 per unit, which is based on the voltage settings which are chosen as basis for a given transformer, no special consideration is needed. This tap position need not be equal to 1 per unit in practical consideration, because transformer taps also help in regulating the reactive power flow through the transmission line. In fact, they are also support reactive power compensation part, which we understood in the previous module. So often you would find taps to be at off-nominal position, where the tap is not equal to 1 pu, and in such case some special consideration is needed before power flow analysis can be applied. So that's all for today's lecture. In the next lecture, we will continue with these assumptions in power flow analysis and understand a critical backbone of how power flow analysis is to be done by understanding what is bus admittance matrix. Thank you.